I will talk about the lie paradox, the halting problem, and the edge of chaos, and I will try to introduce the areas from where I borrowed these terms. It's going to be a little bit complex and eclectic talk, but I'll try to stick with something we've been publishing over the years, except the very last few slides where I will go more into somewhat more speculative material. So the first paper that is included pretty much in this presentation has been already published 4 years ago. It talks about computational undecidability as it is manifested in different computational frameworks, including formal logics, theory of computation, Turing machines, as well as dynamical systems, where cellular automata is a good example of discrete dynamical systems. But surprisingly, for many people, these three computational frameworks have something in common, and that is self-reference. And hence, lie paradox is a motivating example for most of these developments. It's hidden in some of these developments and in some proofs and some arguments, but it is quite important to recognize that the essence of undecidability is related almost immediately and fundamentally to self-reference, and that's what I will be starting about. However, all this undecidability and all this incomputability or paradoxical statements are usually defined and have to be defined within a particular system. Extending beyond the system is somewhat interesting. It may in fact resolve some paradoxes, and that's what I will be talking about later on. But inevitably, it creates in the extended system another version of a paradox. And the second paper, which I will show here by way of acknowledgements, is mostly dealing with, apart from the biological material, it's dealing with that question: what happens when you extend the system in an attempt to resolve a paradox? And I will be arguing, as we did in this paper, that extending this paradox in a biological setting requires the environment dealing as that sort of meta level where the paradox of an existing system is resolved. So that was mostly an informal outline, and formally I will cover these 6 areas. I will start with the topic of self-reference using Hofstadter tangle hierarchies concept informally. Then I will try to get into the halting problem, which is known for computer scientists and related to the lie paradox. Then I'll try to relate it to the dynamical systems and wrap it up with a diagonalization argument, which again is a very well-known argument going back to Cantor, if not before. And then I will get to that description of what meta-level computation or meta-level simulation or meta-level interpretation is giving you in terms of that novelty generation. The final bit, emergence of functional self-description, if I even have time to get there, would be mostly speculative. The very last bullet point here, I don't have anything published and probably never will, but it's somewhat interesting to see analogies going away from computation into biology, linguistics, culture, and in general, preservation of knowledge or preservation of information as a move forward in terms of novelty generation. So let me start with an example which you probably have seen one way or another. We're building towards an impossible staircase that I will have on the next slide, but this is Schroeder's stairs. So it is essentially an optical illusion. What you see on the left with the circle highlighting the actual top of the stairs is exactly the same picture you see on the right. Actual rotation of the picture, you will see what you see on the right-hand side. It's exactly the same picture. However, on the left, you see that circle sitting arguably at the top of the stairs, and on the right-hand side, you see this circle sitting at the bottom. So basically, the illusion which somebody, this guy Sugihara, actually constructed in 3D. He built the model of it with nice, it's actually flat, but if you move it around, you could see that YouTube video. It's actually very interesting. You see that the illusion holds in actual 3D. I'm showing it to you to basically say that the paradox, the illusion appears only in your eyes as an observer because you have a perspective on this particular image. The actual brush strokes, the actual segments of this contour are not paradoxical by themselves. They are just flat 2D surface. It's your interpretation which creates this paradox. Now let's have a look at these two images. Again, starting from the right-hand side, you see here what later became known as Penrose stairs. In fact, Penrose and his son discovered it in 1958 independently, but it has been known since 1937. Oscar Reuterswart was the first who created that kind of picture. So here we actually see a paradox, but I will argue again that this paradox exists only in our minds because what we see is a two-dimensional image, right? The actual brush strokes written or drawn on the flat 2D surface cannot be paradoxical, right? There is no paradox unless you interpret it in one way. So this is an example on the right-hand side of what Hofstadter in his famous book, Gödel, Escher, Bach, called a strange loop. So on the right-hand side is a classical strange loop. What you see on the left-hand side is a tangle hierarchy. It's a well-known, famous drawing hands image created by Moritz Escher in 1948, just in between the strange loop images on the right-hand side. And it's also a strange loop, but it has something else. It's not just a paradox in terms that we cannot find the beginning and the end. It's a paradox in the sense where the emergent level, like the hands are drawing themselves. So this is tangle hierarchy, and as Hofstadter argued, it's an interaction between the levels in which the top level reaches back with the downward causation towards the bottom level and influences it, while at the same time, it is being determined by the bottom level because the hands are drawing the image. So why is it not just a strange loop? Obviously, there is a meta level, like in a strange loop, there is some sort of chicken and egg dilemma, but here, in addition, we have a hierarchy. The meta level, the level at which we make the perspective interpreting the bottom level, is implicated directly by itself. It is being drawn by the subject level, by the bottom level. That's why tangle hierarchy is a little bit more involved in a strange loop. What's in common, though, is that you need to have a meta level which interprets it. Without a meta level, both images are just 2D collection of strokes, right? So that's what Hofstadter also talked in his book, Tangle Hierarchy. On the left-hand side, the concept of self-reference is essentially made explicit rather than implicit. On the right-hand side, there is no self-reference. There is somebody outside, some sort of interpreter. And I don't even mean it has to be a volitional agent, an actual observer. It could be just a level at which the interpretation is made by way of interaction, like particle bouncing off each other. But what's important that on the right-hand side, you don't have self-implicated in this interpretation, and on the left you do. So self-reference is indeed tangled within this hierarchy. So now let's look at the right-hand side again, and here we have a well-known description of a DNA, or representation rather, and it's not visual, but functionally we know that genetic instruction, the sequence, the data are used in development and functioning of a living organism with function and with structure, and this function and structure then are constructed in such a way that it could copy itself and have these embedded instructions within. So the data create a program which then can copy itself using the data. So it's again an example of a strange loop and a tangle hierarchy, because self is implicated here quite directly. Here is another example. It's a well-known problem, the L-Farol bar problem, and Brian Arthur was the guy who put this dilemma forward. Imagine that each agent or each individual in Santa Fe is considering whether they should go that night into this bar. And it is, say, known that if given the capacity and whatever tradition, that if the number of attendees or number of customers in the bar is less than 60%, you'd have beautiful time. But if it's over 60%, you'll have dreadful time. Your question is, should you go or not? And you could have access to historical data of previous attendance. You could make whatever rational prediction based on this number. Imagine that there exists a rational prediction. Then each agent will have access to this prediction because it's rational, and we could all form a decision. If the prediction says it's going to be today less than 60, everybody would go and invalidate it straight away. But if it said, no, it's going to be over 60, everybody would not go, and it would have been empty and probably enjoyed. So it's called a minority game. So again, there is a self-reference embedded in this strange loop because the agent's actions and decisions make the system with the self, with all the self-agents, part of producing this loop. So it's a tangle hierarchy too, because the top level, the attendance record, influences the decisions of the agents, which then affect the top level. Keep in mind, minority game. I'll get back to that question later on, because minority will be seen as an example of negation, not a majority, minority. So that brings me to the classical lie paradox. This sentence is a lie. What's paradoxical about it? Again, the sentence, sequence of characters cannot be paradoxical. It is just sequence of letters in some language. What makes it paradoxical is when the meta level starts to interpret it. When I say this sentence is a lie, I try to ascribe a meaning. Is this true or false? The whole sentence, is it true or false? And if it's true, it must be false, and other way around. So that becomes paradoxical because the meta level interprets it and ascribes the true and false, connecting to what is written here. Why is this significant? For all these computational frameworks that I mentioned in the beginning, that I will be talking about, logics that Gödel worked with, or theory of automata or algorithms that Alan Turing worked with, or even dynamical systems. So Kurt Gödel, people argued, and another very famous computer scientist, mathematician, John von Neumann, basically said in 1951, contribution or achievement of Kurt Gödel in modern logic is monumental. It's more than a monument. It is a landmark which will remain visible far in space and time. In 1931, in fact, he published it or presented in the conference in 1930, but published in 1931, two incompleteness theorem. And the way he proved it used the liar's paradox. That's what makes the connection. So he argued and proved that any consistent formal system with a certain amount of elementary arithmetic, it can't be completely simple, can be carried out to be incomplete. So there are some statements expressible in the formal language of that system that you cannot prove nor disprove using the system. And you could say, what kind of sentences, what kind of statements would that be? And it's exactly the statements which are similar to this sentence is a false, self-referential, lie paradox-like statement. What it means, what it boils down to, that given any system complex enough, you will have either incomplete or inconsistent. So if you include these lie paradox statements in there, you will have it inconsistent. If you exclude them and they're expressible, that would mean incompleteness of that system. So what essentially Gödel has done, he expressed that kind of lie paradox statement, this sentence is a false, in the language of a formal logic system. So he actually expressed, and that's what's called Gödel sentence, that given system F, you could entail the following statements, that some gamma is equivalent, logically equivalent to being not provable in a system. But note the angle brackets around gamma. Angle brackets essentially mean that there is a number, specific number using prime number construction, which corresponds to a statement gamma. So many people, in fact, argued that because on the left-hand side you have gamma and on the right-hand side you have a Gödel number of gamma, it's not really paradox. But once you start thinking and interpreting it, and there are other proofs as well, you will see that it is paradoxical. If you exclude that kind of statement, you exclude that statement on the right-hand side out of the system, it becomes consistent, but then it's incomplete. However, I again draw your attention that this construction, looking at that statement gamma and talking about not proving a Gödel number of it, is essentially an interpretation which occurs at the meta level. By itself, the bunch of symbols does not constitute a paradox. Paradox is created only at the level of interpretation of it, not in the object level itself. However, Gödel expressed it at the level of the logic. So let's leave it at that point, and I'll move on to the halting problem. So what Turing machine is a complete abstraction, and in fact, it uses an infinite computational medium, tape. So you have some medium, tape, on which you could print some numbers, and you could read from this tape. This printing, reading, and writing operation is done by the head of this program, which is positioned precisely at a particular cell. But you could also move the tape left or right. In usual implementation, could be sufficient to move it only to one side. And then the decision what to print depends, and how to move left or right, depends on what you read and the state of the machine. So that's another object. Machine has a state. The program is essentially the number of rules which says, if my state is such and I read such and such letter of alphabet, I do the following action: print and move to another state, my own state. So that is called a program. So here you have data and the program. They're separate. Data goes on a tape, program sits behind the head. It's actually quite curious that when Turing was describing this process, he was not describing it as if it's a mechanism which does it. Basically said, okay, imagine the tape, imagine the head, and there is a person, a dissolute person who does it, moving to the left and to the right and print and read, meaning that there is no way out of it. It's just an automaton, right? Essentially an artifact. Why is this abstraction, which looks almost silly, especially now that we have all these computers and phones and other systems, why is that so fundamentally important? It is so because Turing proved that any algorithm can be implemented using this simple process: reading, moving, writing, changing my state, moving, reading, writing. Anything you can implement as an algorithm could be reduced to that sort of abstraction. There are other similar abstractions which also achieve similar purpose, but in fact their importance is deduced by comparing and proving equivalence to Turing machine. So that's classical benchmark for computation, right? That's great, right? I mean, so we have a machine which can compute pretty much everything we want to compute. However, on some data, some programs would not necessarily hold. It means that, yeah, for some data and inputs on the tape and some programs, you could show that it's provably guaranteed to hold, achieving some state. Whatever final state, you read it out, that's your answer. And for some programs and some data, you could prove that it will actually never hold, it will go in a loop. That's also fine. Okay, you prove it's going to go in a loop. What's troublesome is that for some data and some programs, you cannot answer definitively whether it will hold or never hold. You simply cannot deduce the answer. So that statement becomes undecidable. So it's computational undecidability. I don't want to spend a lot of time on Turing machines, but at this point, I simply show you how it looks like visually, what the output looks like. Look at the right-hand side, and in the alphabet with 0 and 1s, this particular busy beaver machine with 3 states goes left, right, prints something, and the sequence of 1 sort of goes like that and widens, and then it reaches that particular last line with an H indicating that it stopped. The interesting thing happens, given that halting problem and given that Turing machine machinery, is that you can actually demonstrate the halting problem by using self-referential argument. And that's why I want to show it to you. So imagine at the top you have simple Turing machine, just some input on the left, it goes in the Turing machine and eventually it produces some output. So that machine is called M. It could compute whichever, x squared, whatever. But imagine you have a universal Turing machine at the bottom, which takes as input on the tape descriptions of other machines. And that's where you should prick your ears and think, hold on, what does that mean? That means that the description of a machine, description of a program is turned by some interesting encoding into the data. So what is the program at the top becomes the data for the program which is at the bottom, right? Okay, so why is it called universal Turing machine U? Because taking that input of the top machine, it's supposed to produce the output which is identical to the output of the top machine for any given input. So basically it says, get me whatever program, any Turing machine and any data, and I could reproduce it with my universal Turing machine. And you think, well, okay, so it exists. universal Turing machines do exist. But you see that here you create potential for some self-referentiality, because you could say eventually, what if I put the input of myself in there? Would it be all right? And it turns out that it will create a classical paradox in style of the lie paradox. So it goes like that. But imagine that you have a normal machine P, which for any particular input W, it could either accept, meaning it halts, or you don't accept, reject. So basically, halting problem is that you cannot necessarily say accept or reject for any input. But if you assume that such a universal decider exists, it means that you can answer anything. Let's assume it and prove by contradiction that it's not possible. And therefore, halting problem exists. But for some inputs, you cannot fill in the gap. Because if it existed, right, you could come up with the inverter, which is exactly what the top machine does. But then you could do the negation and you could flop. So V is the inverter. So you flop, accept, and reject. And the final beauty, the final step is you fit encoding of V in itself. And that's where the paradox essentially is created, because on the right-hand side, by construction, you get V accepting V, meaning that it is getting rejected. So you see the important steps of this proof were that you flip-flopped accept and reject in constructing the inverter, and then you fit inverter description into the itself. So this sentence is false. That's what it says. You have statements which are going to be undecided. I'm showing you that at the level of detail so that you see how the lie paradox gets embedded in all these constructions, either by direct construction of logical statement or by constructing of this machinery. I'm moving to dynamical systems. And in dynamical systems, if you know a little bit of Wolfram's classification of cell automata, how some of them are going to be ordered or maybe going in the loop, limit cycles, that's class 2, or becoming chaotic. But some statements, some dynamics you can never actually, in a finite cell automata, you cannot demonstrate that they will necessarily reach an attractor, basically repeating itself, nor go in a chaotic behavior which becomes randomness, right? So what you see right here on the right-hand side is a very famous game of life visualization, which builds essentially these gliders. You could think that, somebody wrote, if you don't know what's going on here, you could think of some sort of complicated computer program which draws it in this particular sequence. In fact, what happens is very simple rules which create any live cell if it's not overpopulated or not too lonely, basically between 2 and 3 neighbors. If you have too many or too few, the cell disappears, and any dead cells with exactly 3 live neighbors becomes a live cell. And given the initial state, you could get very intricate patterns created like that. That's what you've seen already. So those are gliders which are created, and you pretty much could marvel at infinity of this thing. By the way, it's supposed to be in the proper implementation, the infinite computational medium. If it is finite, at some point it will repeat itself. It's clear that eventually, after, I don't know, zillions of iterations, it will repeat itself. And obviously people marvel at this game of life precisely because these 3 simple rules, which is totally algorithmic, create new cell, remove a cell, create new cell, remove a cell, given 2, 3, 4, 5, 8 neighbors, could create such a marvelous, complex computational dynamics. I'm showing it to you for a different reason. You could have some attractors repeating themselves, like, pulsars, which is like memory almost. Some go as gliders from a place to play. That's like a communication line here. And I will argue that some initial states, given these 3 rules, will not settle on an infinite medium. We will not be able to prove that they will settle into either a periodic attractor or just frozen, or go into chaotic attractor, right? I mean, obviously, you could imagine that people spent years and years and years playing with this game of life, trying to come up with very complex shapes. Like, this is obviously in a periodic attractor orbit already. Right? So it repeats. So that repeats itself. That probably goes somewhere, but again, in a repeated fashion. So the question is, what do you then say about the states, or the dynamics rather, that you can neither prove to be freezing or going in the limit cycle, nor proving that they stay in a chaotic regime, right? That was the main question that triggered our paper that I'm going through, where we tried to argue that this middle ground, the class 4 automata, are exactly the ones which correspond to undecidable statements of formal logics in Gödel and halting problem of computational theory. It could go on and on and on, and no point spending more time because you got the idea. The question that I'm bringing up here again, is something like that necessarily fixed point or limit cycle? Can we prove it? Or maybe we could have a chaotic or strange attractor. You look at something like that and you don't know whether it will converge or completely resolve into randomness. So basically, the question here is whether we can prove an undecidability of the initial state given as input. And that what is completely equivalent, and we showed it by construction, completely equivalent to the other two well-known undecidability manifestations, one being the Gödel sentence, another being the self-referential universal Turing machine, which we know does exist as a universal constructor, but cannot exist as a universal decider, giving answers to any input. So the analogy in dynamical systems, or at least in discrete dynamical systems, are the class 4 automata. In this case, you see a game of life. It sort of starts to sound a little bit hand-wavy because it's unclear where exactly do we have a negation here, where exactly do we have self-reference, right? I didn't talk about, the discrete automata and cell automata self-referring to itself. I didn't talk about negation. But before doing that, I want to also look at self-reference and diagonalization argument. So what you see as horizontal lines here, this M1, M2, M3, are the Turing programs or cell automata. In this case, it doesn't really matter. So imagine that M1, M2, M3 are different programs, different rule tables for cell automata, or different Turing machines. What you see on vertical with the encoding with the square bracket M1, M2, M3 is the data. This machine's turned into data. So you have a description, you have a cell automaton, or you have your Turing machine program rules. You turn it into the data by some sort of, you convert it into 0, 1. But there is one-to-one correspondence between M1 and the square brackets of M1. Rows are the programs and columns are the data. Now I will construct my liar paradox. I will then assume I could solve any input. Basically, I'm assuming that if there is no halting problem, then I could decide on any input, any white spot here, what would be the outcome that my program will resolve it. So basically, I fill in the gaps, running my machine M1 on any possible input, including, and that's where you again need to be very careful, including the description of itself. So the diagonal is a machine running on description of itself. Again, there is no paradoxes yet. I just assumed that I fill in the gaps, that there is the universal decider. Then I will construct my analogy of a Gödel sentence by saying, okay, there is then a program which takes input M1 and does opposite to what M1 did on itself. So if that was accept, I do reject. Running M2 as an input, I do the opposite of what M2 itself would have done. If it was accept, I reject. If M3 running on M3 was reject, I say accept. I'm just constructing a machine. That's my universal cell automata. And then the question is, what do you put here? By construction, I'm supposed to negate what I would be doing on myself. So you cannot put neither accept nor reject in exactly the same way. You cannot resolve the paradox in any of the systems we looked at. And that's exactly when you look at cell automata, that's exactly what happens here. If you have a description of an automaton, for example, a game of life, you find a description, right? 3 rules, and negate it and feed it as the input state for that automata. You cannot then say, if originally you'd be getting into frozen state, your interpretation now says I'm supposed to go infinite, and vice versa. So here, exactly the game of life, 3 rules. They create these gliders which slowly move in space. And now I'm zooming out. But what you actually see here is a very complicated universal cell automaton. It's called metapixel, not surprisingly, because the smart guys who created it make mind-boggling rules which simulate game of life. As you zooming out of here, you start seeing metapixels emerging. Moreover, these metapixels, as you zoom out, start to look like cells, which themselves could be interpreted by the observer as 0, 1s. And what is quite mind-boggling, what you see right now is a two-dimensional representation of a glider, which not only shows it, it actually moves in time with precisely the same topology, precisely the same replication as the original game of life. So what does it mean then for my construction? I could then ascribe a meaning and say, if the original attractor of the game of life corresponded to true, I could say I flip in my inverter, and what you see at the meta level emerging, I designate as false, and vice versa. And then once I connect my termination condition to yes or no, I get a paradox, but not before. What you see right here is still a pretty picture. Moving picture, replicating picture, replicating itself at a meta level, but there is no paradox in here. Paradox is only created when somebody like me ascribes opposite meaning, true to the bottom level and false to something like this. Only then there is a paradox. What I argued so far, that for undecidability, you need to have three factors. One is a tangle hierarchy, so program data duality, and I use it pretty much in every construction. In Turing machines, I'm feeding the program as data with the encoding, and in cell automata, I do the same. Infinite computational medium is a must. If the Turing tape was not infinite, if my game of life space was not infinite, and if the space where I write logical proofs was not infinite, I would not get my paradox. And finally, I need to have a negation. And obviously, inverter in Turing machine or not provable in logics is clearly negation. But remember minority game? Negation was hiding there with the I want to be in a minority. I want to be in less than 60%. So without a negation, you simply cannot even express it. So those are three factors for undecidability. Now I will go to meta simulation. To reinforce the point on the meta level with the tangle hierarchy, I go back to Hofstadter, to his beautiful abbreviation of jutzing. If you have not heard, it means jumping out of the system. If you are able to do that, it means you are able to expand and extend your system to some other level. So basically your meta level does resolve it for you. That in itself sounds okay, nice, but it's not really going to solve the problem. It simply outsources it to somebody else, to an oracle. But before I show you what an oracle is, I introduce another genius, Emil Post, who actually in 1921 had the proof. He said in a postcard in 1938, after he actually physically met Gödel, that I would have discovered Gödel's theorem in 1921 if I had been Gödel. So he didn't stop though, and in 1944 he published a very fundamental paper on recursively generated logic, essentially showing that you could resolve any paradox by extending the system, by that creates its own paradox in the extended system. And Gödel too had this idea of extensibility. Think of it this way, and that I'm going back to Turing's idea of oracle machines. So what you see in a square is your Turing machine. You have some input and you do through the state transitions, and then you arrive at this question mark. But imagine there's somebody outside of the system, an oracle, who says, okay, that's the answer. You don't know what the answer is. Halting, not halting, I give you the answer, halting. It's not obviously part of the Turing machine. But if you have this, you could then construct something like this. You could say, okay, let's include oracle, which gave me an answer as an axiom. You add it because you extended the system. You could then construct yet another paradoxical statement in extended system. You could continue in infinity with alpha being like first order, second order, third order oracle machines. And an interesting question is, what does it do? What does it do when we extend the system? If you add the meta level computation to these three factors, you then are able to generate novelty. And in many manifestations of that, people argued about novelty generation in biological systems, in linguistic systems, in cultural systems. They all have something in common. You have self-reference, you have undecidability, you extend the system, and that's exactly where you generate novelty. For example, Carl Verze, a famous biologist who argued that there is this transition in biological systems that when you go from pre-RNA world to our RNA and DNA world, the actual transition which happened at that time was comparable to this extensibility. The nature invented the code describing itself. And because you have this program data duality, that was the time when a tangled hierarchy was created. And now a few speculative slides, how the genotype-phenotype relationship had come to be. Before RNA, there were no genotype-phenotype. Cells reproduced vertically. They did not have an encoding of themselves reproduced. Not perfectly, not preserving information. The functional self-description encoding appeared at the point of a coding threshold, at the point when codes became useful, maybe given some noise, which made it hard to reproduce, or given some capacity. But essentially, it was improving the preservation of information. So that was genetic code was a functional self-description. And if I may, I will then argue that in language, the grammar is a code like that. So grammar is created when language capacity becomes complicated enough that without the grammar, it's hard to maintain communication. So the grammar is created or emerges because we're trying to deal with imprecision, uncertainty, complexity. But once the grammar is there in a tangled hierarchy way, it starts to influence how we communicate. So essentially, the language offers a means for a functional self-description. That's speculative, right? Then we're going into culture as a functional self-description of a society. When we go from one generation to another, we start talking about education and preserving information in some other way and trying to maintain law and order and all of that. So culture then offers means for preserving the society, preserving information about the society. So our norms, our conventions, what we call culture in general, is a functional self-description of our social dynamics. Without it, it would be hard to represent. And this is the summary which related computation and undecidability. Undecidability, we argued, is generated by self-reference, infinite computation, and negation. We argued that computational novelty can be created by agents with a universal computation and a functional self-description, and then novelty generation by extending from alpha equal 1 to alpha equal 2, first order to second order to third order. One result which is important for us studying complexity is that complex systems can be defined as dynamical systems with undecidable dynamic. That's where I would like to stop.